It's an airburst. It explodes in the sky above, fortunately, an uninhabited area of Siberia. But the devastation is huge. It wasn't even noticed for some years afterwards until scientific teams went in and studied the area and discovered that 80 million trees across 2,000 square kilometers had been completely flattened.
In 1908, a mysterious explosion leveled over 800 square miles of Siberian forest. This event is now known as the Tunguska Explosion. More than a century later, scientists still debate its precise cause. Now, with the rise of quantum computing and artificial intelligence, some claim that Stanford's Quantum AI may have just recreated the Tunguska explosion. But how much of this is real science, and how much is sensational fiction? Let's separate fact from fantasy and take a grounded look at what Stanford's quantum research is actually capable of, and what really happened in the skies above Tunguska. The Tunguska event. On the morning of June 30th, 1908, a powerful explosion ripped through the skies above a remote region of Siberia, near the Podkamennaya Tunguska River. The blast released an immense amount of energy, flattening an estimated 80 million trees over a vast area of roughly 2,050 square kilometers, or about 830 square miles. Witnesses as far as 1,000 kilometers away reported seeing a flash of light followed by a shockwave that shattered windows and knocked people off their feet. Known today as the Tunguska event, this mysterious explosion remains the most powerful impact-related event in recorded human history, not caused by nuclear weapons. Despite the immense destruction, no impact crater was ever discovered. This puzzling absence initially gave rise to decades of speculation, ranging from exotic natural phenomena to theories involving extraterrestrial activity. So, what was it? Well, the remoteness of the Tunguska region delayed any scientific investigation for nearly 2 decades. It wasn't until 1927 that a Soviet scientific expedition led by mineralogist Leonid Kulik arrived at the scene. Kulik's team expected to find a crater and perhaps fragments of a meteorite. Instead, they encountered a radial pattern of flattened trees and charred trunks with no central impact depression. Trees at the epicenter were stripped of their branches. Still, they remained standing, scorched and upright like telegraph poles, further supporting the theory that a powerful explosion had occurred high in the atmosphere rather than a direct ground impact. Since then, numerous expeditions and studies have sought to understand better what exactly caused the blast. Modern simulations and atmospheric modeling have reinforced the airburst hypothesis. The likely culprit, according to current models, is a stony asteroid measuring between 50 and 60 meters in diameter and weighing around 100,000 metric tons. Entering the atmosphere at speeds estimated to be around 27,000 kilometers per hour, the object would have experienced intense friction and pressure, leading to a rapid and catastrophic disintegration mid-air. The sudden release of energy created a shockwave that propagated outward, causing the tree-flattening pattern still visible today. One of the strongest lines of evidence supporting the airburst theory is the absence of meteoritic debris in large quantities. While a few microscopic particles consistent with meteoritic origin have been recovered from local soil and tree resin, they are not numerous enough to suggest a traditional impact. Additionally, high-altitude detonations produce heat and pressure sufficient to vaporize or fragment most of the entering body before it reaches the ground. This is why no sizable fragments or craters have ever been discovered, despite extensive searches. The Tunguska event has helped scientists understand how even relatively small celestial bodies can cause catastrophic damage if they explode in the atmosphere above populated areas. In 2013, the Chelyabinsk meteor, which exploded over southern Russia, injured more than 1,500 people, mainly due to flying glass from shattered windows, despite being smaller than the Tunguska object at roughly 20 meters in diameter. In recent decades, advances in satellite imaging, seismology, and computer modeling have allowed scientists to reconstruct the Tunguska blast with greater precision than ever before. Studies published in journals such as Nature, Geophysical Research Letters, and Icarus continue to support the asteroid airburst model, with some variations exploring whether the object may have been a cometary fragment composed of ice and dust, which would have vaporized more completely than stone or metal. Nevertheless, experts point to a natural celestial origin. This brings us to Stanford. Stanford's Quantum AI. Stanford University has long been at the forefront of innovation in both artificial intelligence and quantum computing. Through initiatives such as QFARM, which is short for Quantum Fundamentals, Architecture and Machines, a collaborative effort with SLAC National Accelerator Laboratory, the university has focused its resources on advancing research into the next generation of computing technologies. This program brings together physicists, computer scientists, engineers, and materials scientists to work on foundational problems in quantum information science. The Stanford Artificial Intelligence Laboratory, or SAIL, established in 1963, has played a pivotal role in developing early AI methodologies and remains a hub of activity in machine learning, natural language processing, robotics, and neural network design. The growing convergence of quantum computing and AI at Stanford is not merely theoretical. It is grounded in the practical exploration of how quantum machines could one day perform tasks currently deemed computationally prohibitive, such as simulating molecular interactions with extraordinary precision or optimizing intricate logistical systems that involve billions of variables. The idea of combining quantum computing with AI, often termed quantum AI, involves leveraging the computational advantages of quantum systems to process and learn from vast datasets more efficiently than classical computers. Quantum AI is especially promising for problems that involve high-dimensional spaces or require simultaneous processing of numerous potential states. At Stanford, researchers have been exploring these possibilities in controlled academic settings, using quantum annealers and gate-based quantum systems to conduct simulations relevant to chemistry and condensed matter physics. However, the technology is still in its early stages. In terms of what is currently possible, Stanford's researchers have demonstrated the use of quantum algorithms, such as variational quantum eigensolvers, or VQE, and quantum approximate optimization algorithms, or QAOA, on small-scale quantum devices for simulating simple molecular systems. Quantum computing is slowly reshaping how simulations of the physical world might be approached in the future. Stanford and other leading research institutions have proposed using quantum processors to eventually simulate the behavior of high-energy phenomena, potentially including nuclear reactions or asteroid impact modeling. In 2023, for example, IBM unveiled a 1021-qubit processor named Condor, representing one of the largest publicly disclosed gate-based quantum systems to date. Yet, even such systems suffer from error rates and coherence limitations that make them unsuitable for simulating large-scale explosive events with any practical precision. Stanford researchers, like others in the field, are working on improving quantum error correction and developing more stable qubit architectures, but practical quantum supremacy in this realm remains years, if not decades, away. So, what about claims regarding a simulated recreation of the Tunguska Explosion of 1908? Well, that is a whole different story. Debunking sensational claims. In recent months, a flurry of online videos and social media posts has promoted sensational claims that Stanford University's quantum artificial intelligence somehow unraveled a hidden truth about the Tunguska Explosion of 1908. The assertion is that the AI detected mysterious quantum anomalies, encountered unknown energy patterns, or even halted mid-simulation after confronting forces that defied the known laws of physics. So, what is happening? Let's separate fact from fiction. First and foremost, there is no verified report or record of Stanford's AI, quantum, or classical ever simulating the Tunguska event. Stanford University, while a global leader in both AI and quantum computing, has published no scientific paper nor made any formal announcement suggesting such a project was undertaken. The idea that an AI system halted itself during the simulation of an atmospheric explosion due to unexplainable energy readings is pure fiction. No AI developed or used at Stanford, including those under the university's prestigious Q-Farm initiative or its AI research labs like the Stanford Artificial Intelligence Laboratory or SAIL, has demonstrated autonomous consciousness or the capacity to recognize and reject unknown physical phenomena during runtime. Moreover, there is no credible evidence that any quantum simulation, whether run at Stanford or elsewhere, has identified anything resembling a mirror blast, a missing second object, or unusual energy patterns that violate the standard model of particle physics. The Tunguska explosion has been studied extensively by scientists across disciplines, including astrophysics, planetary science, and atmospheric modeling. And while some questions about the precise composition of the object remain, the leading explanation remains firmly grounded in mainstream science: the mid-air disintegration of a stony meteoroid, or possibly a comet fragment, approximately 5 to 10 kilometers above the Earth's surface. Moreover, there has been no detection of vacuum decay, exotic matter, or any form of speculative high-energy physics related to Tunguska, either historically or through modern simulation. The concept of vacuum decay, a theoretical catastrophic event in which a lower-energy vacuum state propagates through the universe, remains strictly theoretical. It has never been observed, nor has any AI system flagged it as a real phenomenon. Quantum AI research at Stanford focuses primarily on solving well-defined and measurable scientific problems. These include simulating the electronic structure of molecules, optimizing energy configurations in materials, and improving error correction in qubit systems. These applications, while transformative in their own right, are entirely different from speculative physics. Quantum simulations are carried out using platforms like IBM's superconducting qubit processors or D-Wave's quantum annealers, and often rely on algorithms such as quantum phase estimation or variational quantum eigensolvers. None of these technologies are presently capable of producing real-time simulations of massive atmospheric explosions with enough granularity to observe anomalies in the fabric of space-time. The propagation of such extraordinary claims is reflective of a broader trend: the blending of hard science with science fiction for dramatic effect. While engaging and often creatively inspired, these narratives should not be confused with actual scientific progress. It's important to distinguish between the genuine capabilities of AI and quantum computing and the exaggerated portrayals often seen in popular media. AI systems, including those developed by Stanford, remain tools designed to perform complex calculations, optimize variables, and analyze data across large datasets. They do not possess consciousness, nor do they have the capacity to interpret metaphysical events. Quantum computers, while potentially revolutionary, are currently limited by coherence times, noise levels, and scalability issues that prevent them from conducting large-scale, real-time physical simulations with high accuracy. But let's say that AI were to simulate the event. What can we expect, in theory at least? What AI and quantum computing can and can't do? In theory, artificial intelligence and quantum computing can, in theory, be combined to simulate and analyze complex physical phenomena that are difficult to model using classical computing. This includes events like atmospheric explosions, meteorite airbursts, and shockwave propagation. AI, particularly through machine learning algorithms such as neural networks or support vector machines, can be trained to analyze past observational data to identify patterns and refine input parameters for simulations. In the context of a high-energy event like the Tunguska explosion, AI could be used to optimize variables such as the meteoroid's estimated mass, likely between 3,000 and 30,000 tons, velocity, approximately 27 kilometers per second, and angle of atmospheric entry, roughly between 30 and 45 degrees, to reproduce the effects observed on June 30th, 1908, when around 2,050 square kilometers of forest were flattened near the Podkamennaya Tunguska River in Siberia. Through iterative training and validation cycles, AI models can reduce discrepancies between theoretical outputs and real-world data, improving the fidelity of simulations. Quantum computing, while still largely in its experimental phase, holds the promise of revolutionizing certain types of simulation. Whereas classical computers rely on binary bits, quantum systems use quantum bits, or qubits, which can exist in multiple states simultaneously thanks to quantum superposition. This feature makes them theoretically capable of processing a vast number of variables and complex equations at once. For example, quantum computers could be used to simulate atomic-scale interactions within high-energy shockwaves, offering more precise insights into the fragmentation patterns of meteoroids during atmospheric entry. Similarly, they could help model the behavior of materials under extreme pressure and temperature conditions, contributing to more accurate predictions in explosion dynamics or impact modeling. Another theoretical advantage of quantum computing lies in energy dispersion modeling. Traditional models are constrained by their assumptions and computational overhead, but quantum algorithms might one day allow researchers to model energy transfer processes with unprecedented accuracy. This could lead to a better understanding of phenomena like airbursts, detonation mechanics, or plasma formation. However, such applications remain largely in the research stage. Despite their theoretical strengths, both AI and quantum computing have important limitations. AI systems cannot see into the past or interact with historical events across time. They are bound by the data and parameters they are trained on. Even the most advanced generative AI models, such as large language models or physics-informed neural networks, are still tools created by humans, trained on datasets curated from real-world observations, experiments, or simulations. They do not possess sentience, intuition, or independent discovery capability outside the bounds of programmed algorithms and data-fed learning. Quantum computers, likewise, do not function as mystical or metaphysical engines. They cannot rewrite their quantum gate logic on their own to account for unexplained or paranormal phenomena. They are built and operated according to the principles of quantum mechanics, and their results are constrained by the initial input, the quality of the qubit systems, and the accuracy of the programming. There is no theoretical or experimental framework in which a quantum system, even under highly advanced architectures like those envisioned with topological qubits or fault-tolerant universal quantum computing, could access or resonate with metaphysical dimensions or previously unrecorded events. Also, AI cannot self-generate new physics. It can extrapolate, interpolate, and model within the limits of its training and programming, but it does not independently create new laws of nature. Breakthroughs in physics require both theoretical innovation and empirical validation. That's why physicists work tirelessly on designing experiments, collecting data, and testing hypotheses over time. While AI can support this process by scanning vast datasets for anomalies, simulating outcomes under a range of assumptions, or even proposing novel experimental configurations, it cannot replace the scientific method. So, where are we currently with AI and quantum computing? Real advancements in quantum AI. Through collaborative efforts like the Q-Farm or Quantum Fundamentals, Architectures and Machines Initiative, Stanford University has been advancing the theoretical and practical frameworks for quantum information science. This includes developing algorithms for quantum simulation, improving quantum error correction techniques, and exploring the integration of AI into quantum workflows. However, quantum computing is still in what researchers call the noisy intermediate-scale quantum era. This means that today's machines, such as IBM's Eagle processor or Google's Sycamore processor, which made headlines in 2019 for its claim of achieving quantum supremacy, are powerful enough to tackle specialized problems, but still too error-prone and limited in qubit stability to support large-scale, fault-tolerant simulations. These systems are currently best suited for proof-of-concept demonstrations in fields like quantum chemistry and materials science. Simulating complex events like atmospheric explosions or planetary-scale impacts is well beyond the capacity of current quantum systems, but not beyond theoretical reach in the decades to come. Researchers are finding productive ways to combine AI and quantum approaches to tackle difficult scientific problems. One promising application lies in quantum chemistry, where quantum algorithms, such as the variational quantum eigensolver, are used to estimate the ground state energies of molecules with potential accuracy improvements over classical methods. Stanford's teams, along with other research institutions like MIT, Caltech, and IBM Research, are exploring how AI techniques, especially reinforcement learning and neural networks, can optimize quantum circuit design, reduce noise, and guide simulation parameters more efficiently. In practice, this means that quantum AI hybrids may soon help identify optimal molecular structures for drug development or predict the behavior of materials under extreme conditions. When it comes to modeling large-scale energetic events, like asteroid airbursts, such as in the case of the Tunguska Explosion, or nuclear explosions, the contribution of quantum AI would likely focus on small, highly complex subcomponents of a simulation. For instance, researchers might use quantum computing to simulate the ionization dynamics of atmospheric particles in the shockwave of a meteoroid entering the Earth's atmosphere at high velocity. AI, in turn, could help tune variables like initial mass, velocity, fragmentation altitude, and angle of entry to match known outcomes, such as those recorded during the Tunguska event. On June 30, 1908, the Tunguska explosion flattened an estimated 80 million trees across more than 2,050 square kilometers of forest in Siberia. The blast, which is widely accepted to have originated from an asteroid or comet fragment exploding 5 to 10 kilometers above the surface, released an estimated 10 to 15 megatons of energy, roughly equivalent to a large thermonuclear bomb. AI-enhanced quantum simulations could one day replicate such a scenario with high precision, modeling everything from shockwave propagation to thermal radiation effects. However, this requires a level of computational maturity and system stability that quantum devices have not yet reached. Most simulations of the Tunguska event to date have been conducted using classical supercomputers and physics-based modeling tools, such as finite element analysis, or FEA, and smoothed particle hydrodynamics, or SPH. These have proven capable of reasonably reproducing the explosion's outcomes by incorporating known parameters such as atmospheric density, meteoroid velocity, and terrain topography. In the realm of quantum computing, real advancements are occurring. For example, in early 2024, researchers at Stanford used AI-driven optimization techniques to assist in the calibration of quantum circuits for noise reduction, which could improve the reliability of small-scale simulations. Meanwhile, physicists at the University of Waterloo's Institute for Quantum Computing have been working on quantum machine learning frameworks that aim to classify complex quantum states, work that may eventually feed into broader scientific simulations. Stanford has the academic infrastructure, computational tools, and scientific expertise to contribute to such an effort. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.